Hi everybody, this is Professor Richard Riley from the Institute of Applied Health Research at the University of Birmingham in the UK, and I'm going to talk here about power calculations for individual participant data meta-analysis projects. And this is based on a body of work that myself and my collaborators have done over the last few years, and I'd like to really thank my collaborators named at the bottom there. So what's the premise here? Individual participant data, or IPD for short, refers to the original, but anonymised, so you don't have patient addresses and things like that, but the original raw data that is recorded for participants recruited to a research study. So it would have information such as their age, their height, their body mass index. If it was a disease situation, you might have their stage of disease, family history, and outcomes for those individuals, such as time to recurrence or death, time to end of the study, and so forth. So detailed participant level information for the study in question. And meta-analysis is where we combine multiple studies. So we're talking about getting the raw data from multiple studies in order to synthesize the IPD to come up with some overall conclusions, for example, about whether a treatment is effective or not, or whether a certain factor increases the risk of a particular disease, and so forth. Now, individual participant data meta-analyses are often quite timely and costly. You can really think about that, can't you? If you think you're trying to get the raw data from people and pull it together and harmonize it and clean it and standardize it and then do the analysis, that's going to take considerable time. So before embarking on an IPD meta-analysis project, it's important to ask the question, is it worth the effort? And what do we mean by that question? Is it worth the effort? Well, what we really mean is, after the potentially long process to get the data and to analyse it, do we think that the data is going to be large enough, have enough information within it, to be able to reliably answer the research question? So, for example, if as a researcher you knew in advance that before undertaking your IPD meta-analysis project, that if you did get the IPD from a particular number of studies, then the power to, let's say, detect a genuine treatment effect would only be 50%, then you might not think actually there's enough there to warrant you doing that research question, given how much time and cost it may take. And funders may decide to prioritise the money towards something else, another project which is more likely to deliver a concrete answer. However, if your IPD meta-analysis project was thought to have a power of, let's say, 8% or more, then funders and yourselves would be reassured, wouldn't they, that the project is worth resourcing, because you are likely therefore to identify the genuine treatment effect, assuming that it exists. In current IPD meta-analysis projects, people don't really think about this issue, and they just proceed and go ahead and do the IPD project. And often when you look back, you go, actually, I'm not sure that this was ever going to produce an answer, because the amount of IPD that we could get, or the amount of trials that already existed, are never going to be able to really reliably address the question that we're trying to address. So this is something I'm really pushing for here, is to think about power calculations and sample size in advance of collecting IPD for IPD meta-analysis projects. Now, that's all well and good, but then we need to think about the mathematics behind this. How do we go about actually doing the power calculation for IPD meta-analysis projects in advance of getting the IPD? Because this depends on many intricate factors, such as how many trials exist, not just how many exist, but also how many trials do you actually think we can get the IPD from, because not all trials are necessarily going to give us their IPD. We need to think about the choice and the specification of our analysis model, because sometimes the type of analysis, and I talk in my other IPD meta-analysis videos about 1-stage and 2-stage, that sometimes can have an impact, as can the choice of assumptions, such as whether you assume common or random effects, such as for treatment, whether we're going to include or adjust for prognostic factors, and so forth. There's a myriad of options that we need to be very transparent about when working out a power calculation. Similarly, the way that we're going to estimate our treatment effect or the estimand of interest, this could be important. So we could use maximum likelihood estimation, restricted maximum likelihood estimation. How are we going to derive confidence intervals? How are we going to derive standard errors? All these intricate aspects are going to have an impact on the power of the IPD meta-analysis project. Fundamentally, of course, power is going to depend on what we assume true effects are. So if we're interested in a treatment effect, we need to think about, okay, what's let's say a minimally important treatment effect that we want to detect, and based on that assumption, what is the power for detecting that size? So in this talk, I'm going to illustrate many of these facets and talk about, in particular, IPD meta-analysis projects for examining treatment covariate interactions. Now, these are also known as effect modifiers. And so we need to understand what these are before we then go on to the power calculation bit. So I want us to be positive and be able to say, okay, I'm going to embark on an IPD meta-analysis project, and based on proper mathematical calculations, I know I've got the power to answer this research question. The alternative is to completely bury your head in the sand and say, oh, it's fine, the power will be fine, we don't need to think about that. But, you know, you might be heading for a fall further down the line if you don't think about power. And increasingly funders will ask you to do this anyway. So I really would stop pretending everything's all right and try and tackle the issue. So going back to the interaction issue. So interactions are where, if we focus on a randomized trial, we want to go beyond the overall treatment effect and say, well, do treatment effects differ for certain individuals compared to others? And many IPD meta-analysis projects indeed are trying to go beyond the overall effect, because we can often address that in a standard meta-analysis without IPD, but with IPD, because we've got the patient level information, we can see individual level relationships better. And so we might be able to say, okay, does the treatment effect seem to be better for people of particular ages compared to others? Is there an interaction between a particular biomarker with the treatment effect? Does the treatment seem to work for some people and not others? So these are questions that go beyond what is typically possible without IPD. So because of this, many IPD meta-analysis projects are set up to specifically examine interactions, and therefore the power calculation should be set up to examine an interaction. An interaction is also known broadly as a subgroup effect if you've got binary covariates, effect modifiers, moderators. And I'm very pro a two-stage approach to IPD meta-analysis, at least when you've got reasonably sized studies. And therefore I'm going to focus today on a two-stage approach to IPD meta-analysis. And this is where, in the first stage, we're going to estimate interactions for each trial separately. And in the second stage, in our meta-analysis, we're going to pool those interactions and primarily going to assume a common effect model, which assumes that the true interaction size is the same in every trial. So a little bit of maths just to put this into context. For a continuous outcome, what a two-stage approach means is that we'd fit a linear regression model in the first stage, where we'd model the continuous outcome like blood pressure, and we'd account for the prognostic effect of a covariate of interest Z. We'd account for the treatment effect, X is the treatment here. We'd account maybe for the baseline value of the continuous outcome, so baseline blood pressure. And our main focus here is this interaction term, lambda, which is interacting the treatment and the covariate. So this interaction term here tells us how the treatment effect changes for every 1 unit change in Z. Or in other words, the difference between males and females if Z was a binary variable, or if Z was age and you assume a linear relationship, then lambda would be the change in treatment effect for a 1 year change in age. So you'd apply this sort of ANCOVA, analysis of covariance model, in each trial separately. You'd take an estimate from those trials of the lambda, the interaction term, and its variance, and then the second stage we'd apply a meta-analysis model where we'd say, okay, let's apply a meta-analysis where we assume that the estimates from all the studies are approximately normally distributed around some true interaction effect, lambda, and the variability is due to the win study variability, which is the variance of the interaction estimate from each trial. And if you fitted this model, you get a weighted average of the interaction estimates. W is denoting here that this is an interaction based on within trial information. We're just using information within each trial separately at the patient level to make inferences. Sometimes people, in my opinion wrongly, also use across trial information and look at relationships between, let's say, mean age and average treatment effect, or proportion male and average treatment effect. But that's looking across studies, and that can be prone to what's called aggregation bias and study level confounding, and therefore I wouldn't recommend that. And this two-stage approach avoids that issue and gives us a summary interaction estimate that is based solely on within trial information. We'll drop the subscriptively from now on, just to avoid extra notation that's not really necessary. So that's what would you be doing if you did have the IPD. But what we want to think about really is, before we get the IPD, how can we work out what the potential power would be? So just if you wanted to pause this talk at this point, you'd be able to see these sets of references. And these references are sort of where the field is at before I talk about the latest piece of research in a minute. So in our book, IPD Meta-Analysis, the Handbook for Healthcare Research, in chapter 12, there's a chapter by myself and Joey Ensor all about power. And this builds on work done by Simmons and Higgins, myself in Stats in Medicine, Joey Ensor in BMC Medical Research Methodology, and two really interesting papers by Kowalczyk and colleagues. I'm going to focus mainly now on these three papers for a continuous outcome, and then I'll broaden things out to a binary outcome in due course. So for a continuous outcome, when we want to think about power, it's important first of all to remember what the mathematical solution is for the variance of the meta-analysis results, and if we can get an analytical solution for that, then we can work back to think about how we could approximate the solution to that if we didn't have IPD. So the variance of the meta-analysis result that I put on a few slides ago. So when you've done your meta-analysis, you're going to work out a confidence interval for the summary result based on the variance, and the variance is defined by 1 over the sum of the inverse variances from each of the trials. So the variances of the interaction estimates in each of the trials are very important. When we follow through the maths, and this is shown in our papers, we get that this is equal to the sum from I equals 1 to k. This is just when there's k studies, so I is 1 to k in terms of the studies, and it's a sum of the n, which is the sample size, sigma, which is the variance of the covariates, and sigma I, which is the residual variance, the unexplained residual variability. So what this means is, actually, if in advance we were able to know what the sample size of a trial is, roughly what the variability of the covariate is, so what's the variance of age, say, and we could make an assumption about what the variability is of the outcome that's unexplained, then we'd be able to work out an approximate estimate of the variance in each trial, and therefore, based on this equation, the overall variance of the meta-analysis results. And then from that, we could work out the power. We could do this in advance of IPD collection, couldn't we? If trial publications gave us the sample size, if they gave us, for example, in a baseline characteristics table, the variance of covariates. And if we knew the variability of the outcome at follow-up too. What's interesting is if you look at this equation as well, we see that obviously studies with a larger sample size will have more precision. This is on the top here, but it's an inverse, so it's going to have more impact. Studies also with a larger variability in the covariate will have more precision and therefore more power. And studies with smaller residual variances will also lead to more precision and more power. So we can't assume that every single trial in the meta-analysis will have the same weight or the same contribution towards the power, because it depends on their sample size and the variability of covariates and residual variances. So we need to take that into account. The power, well, when we do a power calculation, it's a function of values from a standard normal distribution. I'm not going to go into it in detail here, but you can see it's a function of a standard normal distribution test statistics based on the variance of the meta-analysis result, 1.96, the standard value from a normal distribution of the 2.5 percentile levels and 97.5 percentile levels, and lambda, which is the assumed true effect size of the interaction. So if we're willing to specify what we think a minimally important value of the interaction is, and this could be based with discussions with clinical colleagues, and we can pre-specify our sample sizes, our variance of the covariate and our residual variances, then we're in business. We can work out the power. We could also extend this to allow for heterogeneity. So if we did allow for lambda to be different in different studies, we could allow for that. But even though we do consider this in our book, generally I think this is a bit unnecessary because it's making it extra complicated. You don't know in advance whether heterogeneity will be there or not. So why not just assume there isn't, and under the best case scenario of no heterogeneity, tell us the power in that situation. Before I give an example, I just want to briefly mention also an alternative approach. So what I presented there is a analytical solution where you've got actual mathematical equations giving you a solution. A more general approach is to use a simulation approach. This is where you simulate IPD that in some sense represents or reflects the trial IPD, and then you fit repeatedly models to that IPD multiple times and see on average what the standard errors are and what the power is. So you can specify an underlying data generating model for the IPD for each trial, again maybe based on an ANCOVA model. You could specify what the true values of these models are based on information from publications, for example about the control group means, the intervention effects, what you think the interaction is going to be, the size of the residual variances, similar to what we just did on the previous slides. And then generate the IPD for each trial, obviously making sure that the sample size in each trial matches the sample size specified for those trials in the trial publications. Like I say, then simulate that massive IPD meta-analysis dataset. You apply your IPD meta-analysis model to obtain your summary interaction estimate and its p-value, confidence intervals. And then you repeat these previous steps, maybe say 1,000 or 10,000 times. And then the power is simply the proportion of the summary estimates from all those 1,000 or 10,000 meta-analyses which gave you a significant p-value. So that's a general approach. Let's look at an example. So we did an IPD meta-analysis of lifestyle interventions in pregnancy to reduce unnecessary weight gain. We, in advance of the project, were promised IPD from 14 trials, about 1,200 participants. And at the time we didn't think about power, but now I would. So let's just retrospectively go back and say, well, if we could have done a power calculation in advance using these two approaches based on either simulation or analytical expressions, then what would the power have been? Let's focus on BMI. So is there an interaction between treatment and BMI? And therefore I need to think about what aggregate data I'm going to need. So the aggregate data were available to inform the calculations were from each of these 14 trials, the sample size, the variance of BMI, and the variance of the continuous outcome, which was weight at follow-up. And then we got that for each of the 14 trials and applied our calculations. And when we used the closed form approach or the simulation-based approach, we found basically the same answers of 63%. So 63% power to detect a treatment effect improvement of 1 kilogram for every 10 unit increase in BMI. So we pre-specified not just the aggregate data, but the minimally important value was that the interaction would correspond to a 1 kilogram change in the treatment effect for every 10 unit increase in BMI. So 63% power, would we have been happy with that? Probably not. But there were other trials out there, and really what this would tell you is try and get the IPD from all these other trials that are out there, because that would be needed to improve power from 10 additional trials. And that showed that if you did the calculation again, that the power would have been over 80% in that situation, assuming no heterogeneity. So that would have given us reassurance at the onset of the project that our project was worthwhile and that we really needed the IPD from not just those original 14 trials, but also those 10 other ones that hadn't yet promised their IPD, but ultimately we did obtain it. Let's look at this graphically. We see that on the left here is the power, and on the x-axis we've got the assumed interaction effect size, and minus 0.1 corresponds to the results I've just shown you. So the green line is the power for 14 trials, and we see that here at the assumed value it was about 63%. But when we get those extra 10 trials, for the black line, which gives us the power for 24 trials, the power is now over 80%. Clearly, the larger the interaction effect you assume, the easier it is to detect, and therefore the power quickly goes up to towards 100% as the interaction effect size moves away from 0. But for values closer to 0, the power will come down. The blue line shows us the added value of one trial over the 14 original trials, where the one trial was the biggest of the remaining 10 trials. And we can still see that it's still not enough. But you might want to start doing that, other things being equal in terms of generalizability and representativeness, that you might want to focus in on the bigger trials to get up to speed quicker with the power and prioritize those trials with the biggest data in terms of getting their IPD. So I focused on a continuous outcome there, but what about a binary outcome? So this is where I move on to sort of new work. For binary outcomes, we're talking about things like death, yes or no, preeclampsia during pregnancy, yes or no. And we're fitting things like logistic regression models in each study to estimate treatment effects in terms of odds ratios or risk ratios. An issue here, though, is that the residual variances are now a function of the linear predictor of the model, the expected response. So rather than using a single residual variance for each trial that we had to assume before, actually we now need to make it a function of the patient-specific residual variances. Hence I've got this extra J term. This makes it mathematically even more complicated than before. Kowalczyk and Cumberland have some really good papers on this and suggest a closed form approximation where instead of using individualized residual variances, so they approximate that by with the mean risk in the corresponding group. So an individual's residual or linear predictor essentially is set to the mean linear predictor value for the control group or the treatment group, depending on which group they're in. So this is an approximation, and it works well a lot of the time, but not always, and sometimes the error in the power estimates is over 10%, and that's shown in their paper. It's implemented in the R package IPD meta if you're interested. But the major issue I have with this method is that it amalgamates within trial and across trial relationships. Now you remember at the start I said that I want my interactions to be pure in terms of it being based only on the participant level within trial information, and I don't want it to be influenced by aggregated relationships, for example between mean age and overall treatment effect, because they can be different than the patient level relationships, and therefore amalgamating them will lead to a different estimand, and potential bias compared to looking at the within trial relationships only. So that's my concern with those two approaches, with that approach, and we wondered whether we could do something better. So where we came up with is a more exact two-stage approach, which utilises Fisher's information matrix based on a paper by Demidenko in 2008 in Stats in Medicine. In that paper, they provide a solution for a single trial's information matrix when you're estimating an interaction, for example, between a treatment and covariate from a logistic regression model. Here is the solution for the unit information matrix, and it's the expected value over the whole distribution of x and z based on the logistic regression equation and a transformation of that. So this is the linear predictor from a logistic regression equation with an intercept, the treatment effects, the prognostic effect of z, the covariate, and then again here's your interaction of interest. And it also depends on the design matrix X, which is it depends on the sample size of the study and the values of X, Z, and the interaction values for all the participants. If we knew the unit information matrix for every trial, then we can work out the variance of the interaction estimate for that trial based on the inverse of that unit information matrix, which, because there are 4 parameters here, would be a 4x4 matrix. And we take the 4 by 4th element of that inverse of the information matrix and divide it by the square root of the sample size. So in advance of collecting IPD, we can estimate the variance of the interaction estimate if we are willing to specify or assume the values of alpha, beta, gamma and lambda, what the joint distribution is of x and z, and the sample size. How can we do that? Well, again, we're going to base that information on routinely information that's available from trial publications. If we centre our covariate z, this really helps us to think about the interpretation of these other parameters. So alpha then becomes approximately the log odds of the outcome event in the control group. Gamma is the prognostic effect of z. Beta becomes the average treatment effect, strictly speaking the treatment effect for somebody at the mean covariate value, but we can approximate that by the overall treatment effect in the trial. And then lambda, like in the previous example, we need to assume what that is based on a minimally important interaction effect size. So based on summary information, we can get reasonable estimates of the parameters. We now need to think about the joint distribution of x and z. So for a binary covariate, actually what we need to know is the proportion of people that have an x of 0 and a z of 0, the proportion with an x of 1 and a z of 1, proportion with an x of 0 and a z of 1, and a proportion with an x of 1 and a z of 1. So z of 1 is, maybe that's males, x of 1, that's usually with the treatment, and we just need to know the proportion in each of those 4 different categories. Again, we should be able to get that from trial publications or from trial authors. And then the unit information matrix can be decomposed into these 4 different elements, and we can do this very quickly. And if you go to our paper, we've got code in state.r which will run this in just a few seconds for you and calculate the power eventually. So it depends on this equation for a binary covariate, and again, once you've worked out the variance is easy to derive from the unit information matrix based on the 4 by 4th element divided by the square root of the sample size. So just to pause again so that we're all on the same page, what aggregate data are we going to need to do that calculation, to work out the variance of the proposed interaction in each trial separately. We need the total participants in the trial, specifically the total participants in the control group and the treatment group. We're going to need to know the number of outcome events in the control and the treatment group, because this is going to be used to work out the overall treatment effect. We're going to need to know the number of participants in each of those 4 different classifications of Z and X. So this is essentially the joint distribution, and that's it. So that's quite good, isn't it? We can do that. We should be able to get this information, and therefore we can work out the power calculation if we additionally are willing to assume what the interaction size is, which for any power calculation you have to make assumptions about the true effect size. For a continuous covariate, it's similar but slightly more tricky, because you haven't got that nice, neat decomposition of the unit information matrix for different categories of the binary covariate anymore. So what we're going to need to do is simulate a very large data set, and again our data and R packages do this for you. For example, you could have 1 million or 5 million containing the correct distributions of XZ and XZ. And we're going to match X in terms of the number of, or the proportion of people in the control and the treatment groups. Z is continuous, so we're going to have to make an assumption about how we simulate Z. Usually the mean and standard deviation of Z would be available from trial publications or trial authors, and then we're going to have to make an assumption. Maybe it's normally distributed. So for age, we may have the mean age and the standard deviation of age in each of the treatment and control groups, and we'd assume it's normally distributed and simulate values of that. We can then calculate the value of each element of the expectation of the unit information matrix simply by calculating that element for each participant, conditional on their XZ and XZ values and the assumed parameter values, and then calculate the mean of each element, and that's going to give us the expected values, which is the elements of the information matrix. We can then take the inverse and the 4 by 4th element and divide it by the square root of the sample size, and that gives us the variance of the interaction estimate from each trial. So just as for the binary covariate, very similar things are needed. The only additional problem is that we need to assume a particular distribution for the continuous covariates, but then all our code works out all the practicalities in the background. So once we've worked out the variance of the interaction estimate in each trial separately, we can then work out the variance of the meta-analysis interaction estimate, the pooled interaction estimate, based on this formula, the weighted average that we showed before. So we can just plug in our values of the variance of the interaction estimate from each trial, and following that we can work out the power. So plugging in these values to get the variance of the interaction estimate from the meta-analysis results, we then plug in the variance of the meta-analysis results into our power calculation. Again, remember we need to assume a particular true value of the interaction, and it will give us the power. Like I said, we could extend it to allow for heterogeneity, but I think this is unnecessary. Alternatively, instead of focusing on power, we could use this variance of the meta-analysis result to derive a confidence interval and look at the precision of that. And sometimes precision-based understanding of sample size is important as well. But either way, it's the same approach. So let's finish with 2 examples. In this first example, Pernod et al. Examined a treatment, T, versus a control, and they were looking to see whether the treatment helped in the prevention of gastrointestinal bleeding in patients with cirrhosis veracis. They did an IPD meta-analysis and eventually got IPD from 4 trials. Now let's again pretend that we haven't got the IPD, which I personally don't have the IPD, but let's pretend that they didn't get the IPD yet but wanted to know what the power of their approach would be. And we see that we have aggregate data from the 4 trials in terms of the number of participants in each of the control and treatment groups, the mean age and the standard deviation of age in each of the groups, the percentage male in each of the groups, and the number and percentage of events, bleeding events. So this is all we need to do the power calculation. We need to specify the interaction too. So we're going to assume that the interaction is a log of 1.3, such that the odds ratio is assumed to be 1.3 times higher, i.e. worse for males compared to females. So this is the minimally important interaction effect size that we're thinking of wanting to detect. Under the assumptions and based on the aggregate data extracted, the power is 8.8% if we assume that the prognostic effect of sex is 0. If we assume the prognostic effect of sex is corresponds to an odds ratio of 1.5, then the power is 9%. So the prognostic effect of sex doesn't seem to have much impact. If we apply the Kowalczyk and Cumberland approach, their power is 8.7. So in this example, we're getting very similar results. Remember I said that the Kowalczyk approach also used across-trial information. Well, in this particular example, that doesn't have any impact because across trials, there's very little variability. Look at the mean age. It's pretty much 53, 54, 55. It doesn't change much across trials. Percentage males, 70, 76, very similar. So there's not a lot of information actually across trials in terms of variability. So the across trial information has no impact. So the power is not great at all, is it, for sex? But what about age? Again, we use all this aggregate information based on the mean and standard deviation of age, and we're going to assume it's normally distributed. Again, we're going to assume the interaction we're looking to detect is a log of 1.3, such that the odds ratio is 30% worse for every 10-year increase in age. So what's the power? The power is still low, isn't it, for age? 26%, obviously bigger than it was for sex, but still very low. So if you had been doing this IPD meta-analysis project and in advance you knew that the power was going to be this low, you might think twice about doing it. There may be lots of other reasons why you would want to do the IPD project still, and that's fine, but it's important to think about these things head on and to not just assume that you're going to have the power simply because you've got the raw data and you're pooling studies together. It may not always be the case. And we need to confront that and think about that when making our decisions. Let's look at a more positive example. In this second example, it was the STEER OA project, which obtained IPD from 31 trials who were looking to examine whether age or sex modified the effect of exercise for the binary outcome of reduction in pain. Now, most of this project examined continuous outcomes, but I'm just picking out this one binary outcome, which was a secondary outcome. So again, the question is, had they done a power calculation in advance of IPD collection, what would they have found? And I just wanted to disclose that I'm involved in that particular project. So the first step is to extract aggregate data from each of these 31 trials. So I'm just showing you the aggregate data for the first nine trials. And again, just like the previous example, we've got the total number of participants and events for each group, the mean age, the standard deviation in each group, and the percentage male in each group. So that's only the aggregate data that we need, because from this we've got the number of events and total participants. We can work out the odds ratios. We still need to make assumptions about the prognostic effect sizes of age and sex, and generally we're going to just assume that they're 0 because it doesn't have much impact, and we need to assume what the interaction size is. We're going to assume that age is normally distributed again. If you've got, of course, other information to suggest a different distributions, then you can use that. We're going to assume that the minimally important effect sizes for the treatment sex interaction is 1.3, and for the treatment age interaction is 1.027 for a 1 year change in age. So again, applying our code in R and Stata to do this, the power results are as follows. We see that the power is 90% for age and about 40% for sex. So still quite low for sex, although bigger than the previous example, but very, very high for age. Interestingly, the power for sex is partly hampered by sex not being recorded for 2 trials and only females being recruited in another. So there were 3 trials for which you couldn't actually estimate the treatment sex interaction. So the approach accounts for that. And it really illustrates here that you can't assume that the power is the same for every covariate, because it does depend specifically on the covariate's distribution in the different trials. We can also ascertain, again this is in advance of the IPD being collected, the potential contribution of each study. So for age, for example, trials 1, 15 and 28 each provided over 10% of the weight, and if you just did the power calculation including these 3 trials, you get a power of 48%. So over half the power is coming from just 3 trials. So that should flag to you that they are the most important trials to be getting IPD from, other things being equal about quality of trials and representativeness. Having a look at Kowalczyk's method here, we see that actually their approach doesn't tally with ours very well now at all. So they suggested the power was 47% and we got 42% for sex, and they suggested the power for age was 95%, whereas we suggest it's 90%. So why are the differences coming in here? Remember I said that the Kowalczyk approach is an approximation because it doesn't use quite the exact residual variances, but moreover than that, it includes the across-trial information. Now here the across-trial information is influential, and therefore this is why you get this inflated power estimates, because they are willing to use across-trial information towards their calculation, whereas I am not. So the variability across trials, for example, in the percentage male, is now very broad, 9% to 59%, whereas in the previous example, it was very, very similar, wasn't it, across the trials? So that's something to note why we prefer our approach compared to the Kowalczyk approach. Okay, so that concludes this talk. It's been a little bit mathematical, and I appreciate that that may be difficult for some viewers. But the premise is that if you're doing an IPD meta-analysis project, then we do need to think about the power in advance of collecting the IPD. You know, it could save 2 years of your life, because these are not undertakings to start lightly. So really think about this, using either the closed form analytical approaches or a simulation based approach. Have a look at the code that's presented in our papers in R and Stata to be adapted for your particular situation. You'll need to do some groundwork to extract the relevant aggregate data from existing trials, and plus make some assumptions about magnitude of effects, but all this is groundwork you need to do anyway. And I think what you're going to find is that funders are going to ask you, what's the power of your potential power of your IPD meta-analysis? So you're going to need to do this anyway. And you might want to think about a number of scenarios. For example, you know, if you could get IPD from all trials that you know about, what would the power be? That's a bit optimistic. And you know, if you said, well, I'm going to get IPD from these subset of trials that are definitely promised in writing their IPD, then this would be the power, and demonstrate that, then that would also be advantageous. I'll just leave you with this slide giving the references of our particular work, but also see slide 9 for more broader references from Kowalczyk and Simmons and Higgins. So these are our 4 papers in Stats in Medicine, BMC, Medical Research Methodology, and also our book chapter. Do check out our book for more broader guidance on all aspects of IPD meta-analysis projects. And also have a look at our website, where we give entry-level information, some software code, information about training courses, etc. ipdma.co.uk, which I hope you'll find a good source of material. Thank you for listening. I hope this has been relevant and enjoyable, and do check out my other videos.